All right. Well, it is certainly a pleasure for me to introduce Shun Chow, soon to be Dr. Chow. Uh, Shun is at the very last stages of his PhD dissertation, and he's been an asset to our group here, my group at Purdue, for several years, including back with his master's thesis. And I hope I'm not embarrassing him too much to say that he came to us with a degree of master's and bachelor's in physics. And so I had a very stern talk with him when he first arrived at Purdue that this is aerospace engineering and this is not physics, and he needs to understand the differences, and he really took that to heart. And in a short amount of time, he was surpassing some of the capabilities of our students in core aerospace modeling disciplines that had all their degrees in aerospace engineering. And Shun actually, I would say, has also developed into an excellent mentor for younger students. So I could go on and on about Shun, including about the quality of the work that he does and has done and has been instrumental as a foundation for what we contribute to the S2A2 project, which you'll see a little bit from him today. So, but I won't do that because I think you want to hear from him and not me. So I'm happy to introduce Shun Chow for today's seminar.
Then I also second that. Really, he's been instrumental for what we do. Also, he's the source of a lot of wisdom. He shared that with students, and especially my own student here at NCANT. With that, we're going to let him start his presentation.
So, thanks for the introduction from the Professor Durantes, and then for the compromise from the Professor Homifar. Thanks, that's really warm. So let me share my screen really quick. Okay, so I just want to check if everyone can see my screen right now.
Yes, we can.
Yes, we can.
Okay, so I will start. So today's I will mainly talk about the system integration part for the S2A2 project. And just like Professor Darren introduced, he is my advisor, and I'm Xun Zhao from the Purdue University. So let me give a very quick overview about the key activity or objective for this research. So we are trying to define the system of systems that's going to ensure consistent and a clear communication between the researcher and the industrial partner. So we want to make sure that everyone is understanding the project on the same level and then under the same background. So our group that we are trying to create a resource operation and policy economic ensure work table to ensure the consistent taxonomy between researcher and industrial partner. And we will also try to identify some key stakeholder in the work table that can use their point to for the modeling and for the simulation. The next thing we will do is that we will try to identify what's the role for the TC1 to TC3 researcher or their algorithm under the system of system, and in terms of the operational environment or what's the subsystem performance target. So that's the next thing that we will do. The last thing is that we are trying to quantify or qualify the system of system performance with the relevant metrics. So the last thing that we will do in this project is trying to define some metrics and then trying to identify what's its relationship with the algorithm requirement from the TC1 to TC3, and then what's the minimum system requirement we need to draw, and how does that impact the system level performance. For example, the airspace safety is one of the potential key environment or the key performance metrics that we will use to evaluate the effectiveness of the algorithm from the grade TC1 to TC3 and their research. So the approach that we're taking is that the first thing, the whole system of system is very complex and a very complicated system. And in order to understand what they are doing and identify what's the thing we need to model, that we try to build this hierarchical idea over here. So the gamma level trying to depict the whole level of the system, which is the system of the system. Underneath of it, we call it the beta level, which is including the PSU, provider of service for the fleet operator, and the flight controller. So the approach we are taking is that the first thing we are trying to review the FAA and the NASA concept of operation based on the UML1 and the UML4 operation environment. And then the next thing that we are trying to do is that we are trying to model the message exchanging between these stakeholders, what's their key activity, and then what's the state of those actors. And then furthermore, we will also identify what's the role for the TC1 to TC3 algorithm for this activity. And furthermore, we will also identify what's the interface between these algorithms. So the NASA, they have the UML4 document. Under their UML4 document, they identify the several actors. So you can see they including the passenger, aircraft automated system, aircraft, pilot in control, fleet operator, and PSU. However, for the S2A2 project, we believe that we want to move to the fully autonomous vehicle and trying to identify under this condition, what's the other actor in here? Consider the system complexity that we are trying to simplify the model.
How are you typing numbers? I'm using them from the browser. Oh.
Could you mute yourself, please?
Okay, sorry.
Okay, I will keep going. So for the UML5 for the S2A2, we are trying to simplify it. So we are doing a really very quick mapping. So for the passenger, it's still the same, but for the vehicle itself, that we are not considering the configuration of the vehicle. So we are just assuming that we are just only model the flight controller, but just keep that in mind. The flight controller we are depicting over here, including the whole aircraft itself, not just the vehicle itself, but also its automated system. For the fleet operator, we are assuming that we have a pilot sitting on the ground and maybe sitting in the headquarters of a certain flight operator, and the flight operator will monitor the operation of the flight controller. And the last thing, we also have the PSU, and it's will the same from the UML4 and the UML5. So the first thing we are trying to depict is that we are trying to define what's inside the system of system. So we use something, the approach we are taking over here is called the model-based system engineering. And under the system modeling language, that we can construct the first diagram that's you can see over here is called block definition diagram. So you can see, as the name suggests, that the block definition diagram trying to identify what's the correlation between the different actor and the component inside the system context. So you can see that we still have the PSU, we have the fleet operator, we have the flight controller, and we have the passenger. And then the green box over here indicates the interface for the communication of each actors. And you can see for the fleet operator, underneath of it, we have the remote pilot sitting over here. The way we are looking at the system context is that we are following a specific trip and trying to define the state for that trip. But we can see that if we are operating one vehicle in the airspace, if that vehicle run into some trouble and might interfere or affect the other vehicle nearby, so it will affect the other fleet operator as well. That's the reason we have the other fleet operator. So fleet operator indicates the operator which is operating the vehicle for a specific trip that we are following. But for the other fleet operator indicated the neighbor's vehicle and their operator around that specific vehicle and their trip. That's the very high level definition for those actors and their block. And then underneath it, we also define the interface. So you can see we have the communication channel and we define that who should communicate to whom. So we can see we have the communication channel for the fleet operator and the PSU. we have another communication channel of the other fleet operator and the PSU. We also have the communication channel for the operator and the flight controller, and we also have the last communication channel for the passenger and the fleet operator. Here we define that this operator need to this interface need to be exist. However, we do not define which means of the communication that should happen. There could be internet connect, or there could be wireless connect. So depends on the context or depends on the situation. We might have a different detailed definition happen later on. So the next thing that we are trying to do is that we identify those actors. The next thing we are trying to define the state machine diagram for those actors. So the way we are constructing our state machine diagram, that we are not just generating everything from the nowhere. Actually, it's based on the release concept of operation from the NASA and from the AA. So right now we have some, you will see later from the figure, but we have some high-level states such as the pre-flight, in-flight, and the post-flight phase for all of the three actors. And then we also, the most important thing is that we identify the high-level trigger to initiate this kind of state transition. The reason why it is so important is because, for example, if the flight controller is running some issue, we want to make sure that the fleet operator or PSU are aware of this emergent event. So we want to make sure that they are transit to the correct emergent state. So that's the reason we need to define this high-level trigger to make sure that this trigger makes sense and this trigger has been passed through the different action properly. The next thing that we are trying to do is that we are trying to identify how the S2A2 technology can be integrated into this ecosystem. So identify what's the operational context for the S2A2 technologies and identify potential trigger that the S2A2 algorithm must generate for the state transition or something else. And that's what we are trying to do. And then the next thing we'll also showcase is that the detailed logical and the information flow. So for the information flow, we will identify what's the parameter that will be transmitted between this kind of algorithm. So you can see that the information flow also have some information about the interface for this kind of for the S2A2 technologies. So ideally, we will try to provide some summary for the TC1 to TC3 technology, but at this moment, we only summarize the TC2 technology right now. We will keep working on to include the TC1 to TC3 technology later on, but just a very quick overview, what the TC2 are working, and I believe we have some audience from the TC2 group for sure. So if you found that our understanding is incorrect, please feel free to contact me, that we are happy to update our model and trying to depict your algorithm as accurate as possible. But in general, we identify there are four main algorithms from TC2 technology. The first one is that they will have some technology to identify which vehicle is under attack, and by the control dynamic based approach. The second algorithm is that it can identify which vehicle is under attack by resilient convex combination approach. The third algorithm they will generate is robustness against the DOS attack with a switching control framework. So it's trying to detect if there's any DOS attack and how to prevent them. The first one is that we are trying to detect whether our GPS signal has been spoofed or not. So that's the fourth algorithm. And later on, you will see where their algorithm can be implemented among the three actors I just identified, and which activity they need to do, and what's their activity before it and what's the activity after it. So you will see the interface in much detail later on. So that's a foundation, and that's talking about the state machine diagram right now. So right now I need to specify that we are focused on the gamma level state machine diagram, which is the very high level, the system of systems state machine diagram. So for the state machine diagram review that you can see, we define some nominal flight condition, and which is based on the concept of operation. We have a pre-flight state, which under this state that we are trying to generate the the flight plan or operational intent in the concept of operation terminology. They just say the flight plan is equivalent to the operational intent. So they are trying to generate the operational intent, and they're trying to negotiate and share the operational intent with other people, from the fleet operator to the PSU. And if the operational intent is being approved or have some consensus, then the vehicle will start to fly. So we will get into the in-flight state. If the vehicle lands safely without any problem, then we will get into the post-flight state. In the post-flight state, the PSU and the fleet operator will archive the flight trajectory and the flight data for the further or future research purpose. During the in-flight, we know we might have some emergent event that the vehicle or those three actors need to collaborate to resolve. So the first one is really emergent one, which is called contingency cases. So under the contingency cases, we identify one case, we call it the individual aircraft failure. That indicates that one of the vehicle is broken. For example, one of the motor has been broken, they cannot operate properly. Then at this emergency situation, the vehicle need to land as soon as possible. So that's one of the special emergent cases that in the concept of operation document. And then later on, there are another set of the emerging condition, which is called non-conformance cases. So non-conformance cases is that the vehicle can still fly, but due to various reasons, they cannot follow the specific trajectory or the specific operational intent. So those the concept of operation already identified there are several emerging non-conformance cases. One is called all aircraft land. It's like the FAA would like to require all aircraft to land immediately as soon as possible. So that's the case. That's the first case. The second one is called the loss of navigation. So for this one is that due to the radio interference, the vehicle cannot follow the trajectory in a very good accuracy. Then at this moment, how the PSU need to respond to that? The third one is that they found that there are another vehicle which is not cooperative, and that vehicle is interfering with the current vehicle. So that's the non-cooperative aircraft cases. The first one is an unplanned entry to the controlled airspace. Is that we know the UM might get into the airport so that we can provide some airport commuter trip, but due to some reason, the vehicle may get into the unplanned, get into the controlled airspace without the consent or without making the FAA, the air traffic controller, aware of that. So under this condition, how the PSU should respond to that? That will be depicted over here. Another one is aerodrome closure, and it can be through any kind of reason, and one reason could be the weather restriction. So how the PSU or other operator need to respond to that, that's another issue. The other one is the distressed passenger. So the passenger might announce that they are feeling uncomfortable due to various reasons. Under this situation, the vehicle need to find some other vertiport or the aerodrome to land as soon as possible so that the passenger can get some medical service. So at this moment, how the PSU or flight operator need to cooperate, that's it's being depicted over here. This one is the weather restricted landing. Is that during the flight, the aerodrome might announce that their weather condition is very bad, then you cannot land here anymore. So at this condition, how the vehicle need to find an alternative landing site, trying to land as soon as possible. That will be handled or depicted over here. So this non-conformance case is being identified by the NASA and the FAA concept of operation. And in this presentation, I will focus on the nominal operation and then focus on the loss of navigation case as one example. And then for the other cases, our group is working very hard to generate their state and the activity diagram, trying to depict their behavior as accurate as possible. So that's the gamma level state machine diagram. The next thing we are trying to do is that we are trying to define the beta level state machine diagram for the PSU, fleet operator, and the flight controller. So for the for this one, it's a flight controller state machine diagram. Again, we still you can still see the gamma level state over here. So we still have the pre-flight, in-flight, and the post-flight state. And you can see here is a more detailed breakdown about the state for the flight controller more accurately. And then the key thing is that the key takeaway is that we define the nominal state for sure, and also we identify some non-chromosomal cases that we need to define their activity. But the most important thing is that we define those the state trigger that trigger the state transition. So you can see the signal will also appear in the other beta level actor. So this is how we check that whether when some conformance or some emergency happen, whether the state transition is properly and whether everyone will be on the same page. Again, this is a very similar thing, but this is for the fleet operator. We still have the pre-flight, in-flight, and post-flight. So different from the flight controller is that in the flight controller is that for the fleet operator in the pre-flight phase, it needs to generate some operational intent with the PSU. So you can see in the pre-flight, they are getting a little bit busy over here. When the operational intent is being approved, it will get into the in-flight, then their job will become much easier. It's trying to monitor the flight. Whenever the flight lands, it's trying to evaluate the mission completion, and in other words, they are trying to archiving the flight information. Again, for the non-conforming cases, we define several things, but we are still working very hard trying to provide the detail for activity. So we will talk more about that later. The last thing is the PSU. The PSU trying to make sure that every flight has the strategic decompletion or other thing. So for the pre-flight, trying to evaluate the operational intent from the fleet operator. In the in-flight phase, it's trying to monitor the airspace or monitor the flight with the fleet operator as well. And in the post-flight, just trying to archiving the data. For the non-conformant cases, the PSU plays a very significant role trying to connect the different fleet operators together. So it has a little bit more detail and a more complicated stats that's trying to correspond to the different emergent condition. And in our work later on, you will see some example about the state transition, and you will see how we are using this to make sure that the fleet operator, the flight controller, and the PSU are on the same page. Okay, so for the nominal operation, then the first thing I want to share with you guys is that what's the activity diagram that you can see how the activity of those actors are doing. So the first thing we are trying to look at is at the flight controller. So this is the activity diagram for the flight controller for the nominal operation state. And you can see it's kind of complicated at the first time, but actually it's very clean and a very quick way to learn the interaction between the activity and between the different algorithms. So let me show you how you should understand or how should you make sense of this diagram. So at the beginning, we always start from the solid dot symbol over here. And then here is just an initialization for this activity diagram so that we can model or control the flow. The next thing it's trying to do, for example, over here, it says the generate real-time aircraft telemetry. So it indicates that there is some algorithm or some means that it will make the vehicle can generate some real-time aircraft telemetry data. And you can see the dashed line indicated logical flow. So that's the ordering of the activity that the system need to execute. And then you can see there are some solid line that indicate some information will be transmitted or being passed between different algorithms. For example, the generate real-time aircraft telemetry will generate the vehicle state vector. And that information will be shared to this symbol over here. So this symbol indicated the aircraft telemetry will be sent or be shared to the fleet operator and via the fleet operator to a vehicle communication channel. On the other hand, the same information will be passed to the detect loss of navigation system as well. So this activity will try to detect if there's any loss of navigation. And on the other hand, it will try to listen to other information. For example, trying to listen to the non-comprehensive warning from the operator, trying to listen to any neighboring vehicle telemetry data from the V2V communication channel and trying to use the onboard visual sensor to understand what's happening to the environment. It is also trying to detect the passenger whether the passenger is in distress, and trying to, whenever it's true, it will trigger the other state transition. So here you can see the square rectangle over here is indicate the activity that the system need to execute. For example, here it says the identified DOS attacked on the V2V communication channel. So this is one of the TC2 algorithm that they need to provide this kind of activity or the capability to the controller. And you can see it will receive the information from the V2V communication channel and maybe from the visual sensing as well. So this is how you should read this document. And then for the rest of the thing is just trying to define the ordering of the checking on emergent state. If there is any condition thing happen or depict, it will get into this box and trying to trigger the specific the emergent trigger signal, and we will use this signal to trigger the state transition for the flight controller, and those signals will also be sent to the operator or even to the PSU to make them have a proper state transition as well. So the key takeaway from this one is that we can use this to identify the key signal to the activity. For example, we need to detect a system failure. We need to detect whether GPS spoofing. So you can see the detect GPS spoofing should be coming from the TC2 algorithm. We need to identify whether the DOS attack is happening on the V2V control channel. So again, this is the TC2 algorithm can provide this capability. And we can also identify whether there's any attack vehicle nearby. So this activity can also be achieved by the TC2 algorithm. We also identify what kind of information flow that the TC2 algorithm will receive. For example, right now we just have a high-level description that we need a state vector, but later on we will have define a more detailed protocol about for example, what do the V2V communication channel need to have, or what do we mean by the state vector, and what do we mean. Does that include the XYZ, but also does that include also the raw yield and then pitch angle? So this kind of definition is we need to achieve and need to reach to consensus for the S2A2 project. So again, it's just some other review that we also have some priority of the condition event. So right now, for our current setup, we are saying that the system failure is the most important. If that happens, we need to make the vehicle land, and also passenger in distress also very important as well. The next thing we think is the important case is the DOS attack on the V2V channel, and the GPS spoofing attack detection will be the third one. And if these things are working properly, then we will detect whether the neighboring vehicle is under attack or not. So that's for the flight controller. The next actor that we can look at is the fleet operator. So you can see this chart that's saying that the fleet controller, whenever it triggers any signal, it will be sent to the fleet operator, and then let's see how the fleet operator responds to that. So for the monitoring flight condition, it's very similar. We start from this one and we initializing the cases, and then the fleet operator, they are trying to detect some inclement weather, and if there's any inclement weather happen, then they need to respond to that. But another thing very specific for the TC2 algorithm is that the fleet operator will receive a lot of vehicle telemetry from its fleet. So at the meantime, it also needs to detect if either one of their fleet is under attack. So that's the reason we put the detect any attacked vehicle activity block over here. And then I will also specify that the TC2 should provide some service for the fleet operator to detect if there is any vehicle in their fleet is under any cyber attack. If that happens, it will trigger some state transition and saying that we need to send some signal to specific person, to either to the vehicle or to the fleet operator. And then for this one, it will also relay the accurate telemetry data to the PSU as well. So the PSU will be aware of what's happening over there. Another thing the fleet operator will also listening to is that it will listen to any warning signal either from the vehicle or from the PSU. So from the vehicle case that it will listen to if there's any system failure warning, and then if the and also for this one, if the vehicle found that itself does not follow the run into the non-conformance cases, so that information also from the vehicle, and also it will also receive the signal saying that the secondary navigation system is being activated. So the operator will also listen to that signal as well. Or if there's any radio interference happening, the vehicle will also announce that to the operator. It will also listen to any condition case or signal to the PSU as well. If their vehicle get into the control airspace without the notifying the air traffic controller, the PSU will also notify the operators, so via this channel as well. And also, if there's any path conflict between any operator or any vehicle, the PSU will also send that information to the operator, and the operator will respond to that. So you can see by doing so, we can show the different cases or the signal that the PSU will receive or respond to it, and then in the graphical manner, and to see what kind of other signal it will be triggered and transmitted. That's for the operator, and the last thing we will look at is look at the PSU, how the PSU, the nominal operation will look like. So again, the PSU will be the center node, and it will try to receive any warning signal from the fleet operator. Here we are just using the single node, but actually it should be listening any warning signal from a lot of different fleet operator. So those warning signal, like the loss of navigation signal in the individual aircraft failure or non-conformance warning, and here you can see there are some graphical representation and trying to depict it. If which signal coming, then what the station should looks like. At the meantime, the PSU will test if there's any. It will test if there's any vehicle which is not cooperative, or if the vehicle entered the ATC airspace accidentally. At the meantime, it will also listen to the signal from FA if they require all aircraft to land as soon as possible, and if there's any drone closure due to any kind of reason. If either one of that happen, it will trigger either the condition event and send some signal to the fleet operator or to the specific fleet operator to trigger some state transition. So everyone will be aware that we need to be in some condition cases, and everyone will be on the same page and ready for the further communication. So what I just talked about is just for the nominal cases, but for example, what happens if loss of navigation happen? And that's what I will show you guys in this chart. So in the concept of operation document, for loss of navigation, there are two cases could happen. The first one is the navigation equipment failure. At this stage, the concept of operation saying that the vehicle should have some backup navigation system. So it will just switch to the backup navigation system and continue its original operational intent, which means that there was no change to the flight plan. But for the other cases that we might run into some radio interference happen, and which the radio interference might also make the backup navigation system become unusable, because both of the system may rely, for example, on the GPS signal. But if the GPS signal has been interfered by any kind of reason, then the primary and the secondary navigation system cannot be used. Then at the same time, the flight controller need to switch to the backup navigation option or other plane. So the overall procedure is that the first thing, the aircraft will try to switch to the backup navigation option. For example, inertial navigation system could be one of the options for that, because it does not rely on the radio signal from the outside or other vehicle. And we are also assuming that the V2V, the G2V communication channel still be functional, so the aircraft can still send its state to the fleet operator or even relay that information to the PSU. Later on, the fleet operator will announce that situation to the PSU. So the PSU will provide some navigation recommendation to the vehicle, so that saying that, oh, I'm aware that your navigation accuracy may not be as good as before. So maybe there are some recommendation for you. You need to increase your distance from the other obstacle, or there are some obstacle in front of you. You need to be aware of. At that time, the fleet operator will decide whether the non-compliant aircraft should update the operational intent or not. The reason why it needs to update the operational intent may be in front of it, there are some corridor which have very narrow throat that the vehicle need to go through, but because of the navigation accuracy, it cannot make sure that the vehicle can go through this throat without violating the airspace regulation. So at that time, the flight operator may want the vehicle to go into a more open airspace, trying to make sure the vehicle can, under the lower navigation accuracy, can still be safely fly and without create any trouble. So if that situation is being identified, the fleet operator need to update its flight, the optional intent, and then send that to the PSU. And the PSU will review the flight plan and try to also notify other affected fleet operator due to the new the flight plan. So the new operational intent might interfere or have some past conflict with other vehicle, then PSU need to take care of that. When everything being set and we can make sure the new operational intent, before that, if the fleet operator decides the situation is too dangerous, the vehicle need to land as soon as possible, the fleet operator can also send that set of the optional intent to the PSU, and the PSU will ensure that the emergency site is clear and for the vehicle to land. Whenever the PSU and the fleet operator has some agreement about the optional intent or optional plan, then it will just send the plan or intent to the flight controller, and the flight controller will just follow the new operational intent to its destination, either a detour to the original designated destination vertiport, or it will just go into the other emergency landing site. So that's an overview of the sequencing for the loss of navigation cases. So going to a more detail, so this is the flight controller state machine diagram. So originally we will be in the nominal operation state, and then it will trigger the loss of navigation signal. So the flight controller will get into the loss of navigation state. So in here you can see this. We name the activity as the activation of the second navigation system or option. So here for the nominal operation cases, what the information flow will happen. So you can see the blue shaded area is indicated the information flow for loss of navigation. So the core is here, the detected loss of navigation. So it will take the vehicle state vector over here, and it will generate whether the navigation equipage is failed or if there's any radio interference happening over here. Whenever if this situation is being identified, it will be sent over here and to generate a proper trigger to trigger the state transition. So let's dive into the detect loss of navigation activity and see what's inside there. So here is we receive the vehicle state vector, and then the information will be sent to the two boxes over here. The first one is a detected navigation equipage failure. We identify this activity need to be performed, but right now put a question mark over here, indicates that we do not know who will execute or do this kind of detected navigation equipage failure activity over here among the TC1, TC2, and TC3 algorithm. However, for the other one, we found that the activity also need to detect if there's any GPS swing happening over here. So we already identified this activity will be performed by the TC2 algorithm, but we want to make sure that our understanding is correct. So right now we still put a question mark over here. It's just that we need to confirm that with the TC2 partner in a more detail later on. So whenever either case is being identified, this information will be sent out, and you can see the data type is a Boolean over here. And here is just trying to make the trigger happen. So basically, the idea is that if either the navigation equipage failure or radio interference is true, then it will make the it will generate the loss of navigation signal and just send the information to trigger the state transition, and then further on the information will be relayed to the fleet operator. And then for this one, it's the state machine diagram for the flight controller. So the loss of navigation signal will be triggered, and we will jump to the activation of the second navigation system. So here you can see that for this one, if the navigation equilibrium failure is happen, then we are trying to switch to the backup navigation system and then send that information to the operator, and the operator will be aware what's the current status for the flight controller. For the other cases, that if the radio interference is happening, then we need to identify the level of the navigation degradation. So we don't know who will perform this activity, but we think that this activity need to be executed by some algorithm. The next thing, we're trying to activate other redundant navigation option. So just like we said, the option could be the INS, or it could be other option that we are not aware of right now. So if anyone have any idea about what kind of backup navigation option should be, just feel free to let us know. We are happy to put that over here. So based on the new navigation option, we might generate the new other real-time accelerometry data, and then also send the first thing, we will send the radio interference signal to the operator, and the next thing, we will also send the accelerometry data to the operator as well. And then it will try to continue to fly the vehicle under the redundant navigation option. The next thing is that what's the response for the fleet operator? If the fleet operator decides that the vehicle should change its operational intent, it will receive the operational intent and then update that and go back to the original flight condition. But if the fleet operator is saying that, okay, also the navigation accuracy is not good as before, but the situation still be tolerable, you can still fly in, there's no need to change the flight intent, the fleet operator will also receive that signal and continue its flight. So we also identify the key takeaways that we identify there are three activities need to be performed, but right now we are not sure which TC will work on these functionalities. And of course, we believe that as the project go on, we will understand it even more, and we can put some name over here. So that's for the state machine diagram for the flight controller. And here we are looking at what's happened to the fleet operator. So the fleet operator will be triggered from the modified flight to the negotiated new operation intent state. So again, it's just listed the procedure that the radio interference the condition event has been identified, and what's the step the fleet operator need to execute. So basically, it's received interference signal and the accelerometer data from the flight controller, and it will also relay. The first thing it will do to send that information to the PSU as well. PSU will provide some navigation recommendation to the fleet operator, and the fleet operator will analyze this recommendation and also the situation for the aircraft, and trying to decide whether we need to update the operation intent or not. And we identify there are some activity need to be performed by some algorithm, but right now we just put the question mark over here. But the key takeaway is that by defining the activity diagram, we can identify which activity that need to be executed and what's the gap that we need to do and to make this thing happen. So we just identify this thing over here. The last thing is what's happening to the PSU. So basically, the PSU will just originally it's in the monitor flight, and if it's receiving this kind of loss of navigation warning signal from the operator, it will change into the receive and the negotiate optional intent. So there are so many cases, but if the signal is fall into the radio interference cases, then it will basically just trying to identify which other vehicle are affected, and then if there's any path conflict, trying to send information to the other fleet operator and trying to generate the flight path recommendation to the other flight operator. So how should we execute this activity is still a question mark, but I believe the either the TC1 or TC3 algorithm might be able to make that happen. So this is, in general, I want to give a very quick conclusion about our current work. That's what we have done over here is that we generate the state machine diagram for the three actor, the flight controller, the fleet operator, and the PSU. We also generate the activity diagram for identify the key activity under the each state. And we identify, right now what we have done is that we identify the potential activity for the TC2 algorithm can satisfy or can perform. And we also identify the potential interface between the S2A2 related algorithm, specifically for the TC2, and how can them be integrated in the UM system of system. For the future work that we were trying to, right now we are trying to understand the TC1 and the TC3 algorithm from the quarterly report that you wrote, and we are trying to document your algorithm. And I think in the near future, we'll send some meeting requests to you so that we can discuss and to make sure that our understanding about your algorithm is correct. Later on, we are trying to keep working on this activity. Right now, I just show you the loss of navigation case, but you can see from the gamma level state diagram, we have more contingency cases that we need to take into the consideration. We will build an activity diagram for them, and we are trying to test it and trying to debug, make sure the activity diagram is correct and there's no trouble. And then after we finish this, the MBSE model, the activity diagram that we are just going through will be a blueprint for us to generate or to build some simulation model. And with that simulation model, then we can analyze how the different algorithm-based performance requirement affect the system level performance, like the UM system of system safety. That's one of the potential metrics that we will use to assess the UM system of system performance. So that's it for my presentation. And if you have any questions, just feel free to send your message to me or send an email to me. That's also fine to me. So I welcome any kind of feedback or question from you guys. And thanks for your time. And I am ready to take any questions.
Thank you so much, Sean, for this detailed presentation. Okay, any question from cyberspace? Okay, while folks are... oh, go ahead.
Hello. Hi, Sean.
Hello.
It's a nice presentation. I'm Rinmoy. So I have a couple of questions. So in your activity diagram, you have mentioned that there are some components that you don't know which TC is going to work on that. And you have identified some of them that TC2 maybe going to work on that. So do you think that the question mark that you have put here, all of them will be taken care by this S2A2 program, or some of them may be completely out of the scope of this project?
So we believe some of them is out of scope of this project, but right now we are not sure which one is it. And maybe there are some options, for example, depends on what we are using for our flight controller. For example, if we are using the Pixel Hawk 4, that's one of the controller that I'm aware of. But if they have some capability that can replace some of the activity block that over here, then that will be good. Then we can ensure that we have some offshore product that can satisfy this requirement. So not all of them will be the S2 under the S2A2 technologies, and maybe the TC4, our Georgia Tech colleague maybe can teach us, let us know that hey, some of the activity, the Pixel Hawk or some controller, they already have this functionality. Then we do not need to develop that from the S2A2 project.
Okay.
Does that make sense?
My other question is the functionality. It makes sense. My other question is you have identified that some of them will be taken care by TC1 or TC2. So did you collaborate with them or your group to see how they are giving you the output, and if that is aligned with what you are thinking?
So for this one, let me clarify something. So the first thing, we only collaborate with the TC2 right now, and we have some meeting with them and to understand that our understanding for their algorithm is correct. So we have a higher confidence that we can identify the position for the TC2 algorithm in more confidence. But for the TC1 to the TC3, we are still in the early stage to review their quarterly report, and we are preparing in the near future, we are preparing to request some meeting with them so that we can make sure our understanding of their algorithm is proper, and also the potential location of their algorithm inside the activity diagram is correct as well. And after that, you can see the input output, whether the input output is consistent and whether their expected input output create any conflict with the TC algorithm. That's for the future discussion. But in the near future, we plan to have some conversation with the TC1 and the TC3 group for sure.
Okay, thank you.
Yep.
Okay, let me ask also a couple of questions. The first question is, have you looked at the impact of more than one fault in the system, especially on the communication? How long is it going to take for the provider of the service to let everyone else to know?
Yes, Professor Homenfar, that's a very good question. And we were thinking to include if the multiple contingencies happen at the same time, then what's the state for the operator or for the flight controller need to do? But right now we run into a difficulty is that the problem complexity will just increase too fast, and then we cannot manage it properly. So our current work is that we only consider one contingency at a time. So which means there's only one contingency happen. But if we can finish this task on time, and then we are interested in looking at it if we have a multiple contingency event happen and how the PSU or operator need to negotiate or resolve that. So that's what in the future and that's need to do, but right now the complexity is just too high, and we do not have enough resource to work on that yet.
Okay, do you think the issue is the manpower or the issue is the technology?
I think the issue is the problem complexity. So we do have enough manpower to work on the model building up. But however, if we need to consider the multiple conditions happen at the same time, for example, if the weather and the radio interference happening at the same time, that's one example, then how should we resolve that? It will require great amount of the digital review to see what the other people have done, and need to see what the other technology might resolve in, and to discuss or to imagine how the PSU fleet operator and the flight controller need to respond to that, and whether the resolution will come out also be consistent with the optional concept of operation from the FAA and the NASA. So you can see there are so many tests that we need to do, and we believe that for current step that we need to have some working model first, and then we are taking the extra this kind of multiple contingency happening at the same time scenario will be the extra value for this model. So that's the reason we push that to the later on. Right now, we're just focusing on have some working model first, and then we are trying to improve and enhance that later.
Thank you.
Yep.
Any question from cyberspace? Okay.
Hello, I have a question.
Hello.
Please go
You hear
ahead.
me? Yeah, I am Nagasa. I have one question. You are using the state machine, all right?
Nagasa, go ahead and ask your question.
Do you hear me now?
Yeah, I can hear you.
Yeah, you are using the state machine, right?
Yes, I'm using the state machine diagram.
Okay, yeah. So the state machine of the one big problem that is the scalability and the state explosion. So how do you consider these things?
Yeah, so okay, let me say in this way. The state machine, the one of the difficulty for the state machine diagram for the scalability is in terms of the number of states in the state machine diagram. But right now, I think we have a manageable number of states for those actors. So it's not creating too much issue for us. And if we are not introducing extra state over here. So right now, the size of the problem is manageable for the work that we're working on. So we do not think that's too much trouble for us.
Okay, so for example, if the PSU is preparing some client intent for from the operator, there may be the money operators. So isn't the money status available? Can you manage those status?
So I think your question is that if the PSU
Yeah,
is working with multiple operator, then
yeah,
how will that make the state become much more?
yeah.
So yep. So my response to that is the state machine diagram that you are looking here is for a flight. So for the different flight, that the flight can be in a different state. So for each flight, we have still the same number of states, but for the different flight, they may be in a different state. So I don't think that will create much trouble for us. And let me go into the slides before at the beginning. So let me show you these slides. So the reason why we have the fleet operator and the other fleet operator is because we are aware that our approach is trying to follow a specific flight, but we also have other vehicle might be around us and in a different state. So in order to connect the two different machine happening at the same time, we use the fleet operator and the other fleet operator as the interface. And in you can see from my presentation, I show you that the PSU, if the one of the fleet operator update its flight intent, the PSU will identify whether the new flight intent will affect the other operator. So that's the reason we have other operator, and the other in the perspective of other operator, they will receive that information and then have some proper response to that. So by doing so, for the PSU, their state is still the same number of states. They will not grow exponentially. And then we still this fleet operator, other fleet operator, as the interface to connect the different flights together. So we believe that we will not run into the exploding number of the states for the PSU, for example.
Okay, thank you. And
Yep.
my last question is on the loss of navigation. You have said that we can use the vehicle-to-vehicle communication.
That's one of our assumption, and actually that assumption is coming from the concept of operation.
Yeah, but as it is stated in the NASA scope concept of operation, we cannot use the vehicle communication due to ADS-B frequency limitation. So how do you consider this issue?
Actually, we do not consider that condition because I believe in the NASA concept of operation, they said that the vehicles still have the communication capability, and we interpret the communication capability as they have the ground to vehicle or vehicle to vehicle communication capability. And you might be right. I mean, maybe they just lose the V2V communication or maybe they will lose the G2V communication, but that will be extra scenario, and that we just do not consider it over here right now.
Okay, thank you very much.
Yep.
Okay, any other question from cyberspace? While they are thinking, let me ask you also this question, Shun. Imagine that
Yes.
now it is our second annual meeting, because at the first one they were asking a question regarding UML, basically level. You mentioned about FAA UML level 1 and NASA UML level 4. So now your intent is for UML level 5, is that right?
Yeah, that's correct.
Okay, and then so is this something that we should also let other TCs to know about this? Because there was an inconsistency regarding some of the presentation. Some of us were thinking about level 4 or different. So for this time around, we have basically assuming the complexity and all the environmental and also congestion as part of this state diagram that you mentioned.
Okay, so let me respond in this way. So I agree. I think Professor Homenfeld, what you are saying is correct. That I believe this project need to be consistent in terms of which UML label assumption that we are need to follow, and for the TC4 and especially for the Purdue group, that we are flexible to including any kind of UML label. That we just need to update our model to correspond to different label. And then the reason why Purdue team over here that we are using the UML5 is because UML1 is the prototyping stage. Of course, it's not what the S2A2 the project need to solve that level of the problem. For the UML4, I think it's just automated, and they still have some pilot vehicle. They have still some pilots on board on the vehicle under their assumption. So we think that the UML4 is good, but maybe it's not a problem that the S2A2 project is trying to intend to solve, because we are focusing more on the autonomous vehicle. And that reason we are trying to focus on the UML5, which is high. I think in their description, they mention it's a high density urban operation and also highly automated system. So we take that as an autonomous system, and we think that is consistent with the project scope of the S2A2. So we definitely would like to have more conversation with the other TC and trying to make sure if everyone is on the same page. If other people have a different opinion, and if their opinion makes sense, then we are flexible to change our model according to that as well.
Okay, thank you.
Yep.
I have one more question, if it is okay. You mentioned about you are also assessing the impact of weather on UAM operation. And then, do you have any model from NOAA that you are basically that you have developed that you can share it with other people?
Professor Homenfeld, can you repeat your question again?
Okay, remember, as part of your expertise, you mentioned that your work, you mentioned that you are working on assessing the impact of weather on UAM operation.
Oh, weather impacts on the UAM operation. Yes.
So do you have have you developed a model?
Okay, so for that one, okay, so that project is, so that work is from the other NASA funded project, and it's still ongoing project, and we call that the optional limit project. So for that one, it's a data-driven approach. So we are not doing the modeling. we are just collecting the weather data and then apply that to one of the metropolitan area and to analyze how the different weather might impact the UL operation in that specific region. For example, we have some published the paper. So one of the weather paper is talking about how the weather impacts on the Chicago and in the Dallas region. So in that paper, you can see which type of weather phenomena will affect the landing and taking off phase of the UL operation. So that one is for the metropolitan area level of the analysis. So if you are interested, I can share the link to that paper to everyone later after this meeting. And maybe you can take a look at that and to see whether if there's any information that you need or want to learn more, then I can share more information or some raw data with you for sure.
Certainly, I would really love to have that link because, as you may know, Mrimoy and others in the lab are working on this. So maybe we can talk offline about this.
Sure, no problem. I will share that weather, the weather paper link to you.
All right, thank you. Okay, is there any question? We have very fortunate to have one of our, a couple of our advisory board in here. Is there any question from the scientific advisory board to shoot? Okay. Or is there any other question from any other on the cyberspace? If not, we're going to thank Sean. We really enjoy your talk. It was very detailed and very informative. Thank you so much. Thank you so much.
Thank you, Professor Homer.